I do deform so differently, and I was kind of waiting for. But the thing I always told myself about both of those is like, okay, like I could imagine. So I teach it this way. I could imagine, and the majority of people teach it a different way. I could imagine people being like, we should have done it this other way. But if it was the opposite, if most people taught it the way I do and I taught it the other way, um, I can't imagine any case where anybody would say like you're missing out teaching it, in the other form. So when I think about it that way, I'm I just think of it as like this is the way everyone eventually will do it. There's inertia or whatever, but there's really just no real downside except the fact that it's different from what the way a lot of people do. For the people going to the U who are going to take aerospace structures, which is something all aerospace people take, and a lot of mechanical engineers take too, and a lot of civil engineers take. Um, you basically go into that class already knowing so much of what they're going to do. Like that's basically just a class where they translate the old way into the matrix way, and you'll already be comfortable with that. So okay. Um, so exam 3 is on Monday. And the topics are everything. So remember to be ready for stuff from the beginning up through linkages.
Is linkages the only new topic we've had since the last exam?
On the last exam, did we have rigid bodies?
No, we didn't.
Yeah, so rigid bodies and then linkages, but linkages kind of encompass both of them. Um, okay, so we're going to get to something new today that won't be on there. Any questions about the test? All right, so I want to say one last thing about linkages, and this is not something that you'll ever have to do in problems, but it's something I just want you to see and think about for a second. So, on a lot of the example problems I give you, I tell you that the angular velocities of the two bodies at the instant we're looking at are zero, right? That simplifies some of the calculations a little bit. I mean, it doesn't simplify it conceptually. It just takes some terms out of the watermelon equation, so it makes it a little quicker to do. But I could also specify in problems that the angular velocity of this body is this, and the angular velocity of this body is this. Okay, so think about a problem like this for a second. Let's say we have a bar connected to the ceiling here. And then like a different length member connected to a pin and slot joint here. Okay. And let's say that at this instant, so what if it said at this instant, call this one member 1 and this one member 2. Omega of 1 was equal to negative 10 radians per second. Okay, so think about what's happening with member one. Is that moving clockwise or counterclockwise? Clockwise. So that's saying that this structure is like flattening, right? And let's say that I said that omega of member two is negative 20 radians per second. Okay, so what is that? So what direction is member two rotating at this instant? It's going clockwise, which says that this structure is, instead of flattening, that says that this structure is straightening out. So there's a mismatch there. I can't just assign two numbers to this if I'm making these problems. This is not possible. So if I was giving, if you saw this problem, the way you might see it is that they might specify that member one has this angular velocity and just leave it at that. Intuitively, I think you can see that if you specify the angular velocity for this one, it actually specifies the angular velocity of this one too. We don't know what that number is off the top of our heads, but if this is doing one thing, this can only do one thing. Okay. Another way of saying that is this is a 1 degree of freedom system. There's only one control variable that you can use to determine the position of this system. Okay, so how would we come up with that? So for example, if we're given that the angular velocity of 1 is equal to negative 10, how would we determine the corresponding omega 2? Anybody have any guesses about how we would do this? It's similar to something that we've done with accelerations, but we're just, what? So yeah, you have to use relative motion and circular motion. And the basic idea is just like with the, I don't know why I put this here. Just like with the acceleration constraints. So just like the acceleration joint constraints, we'll put constraints on the velocity vector at chosen points. Okay, so for this setup that we have here, what are the limits that we're going to put on the velocities at certain points? So if I call this joint A, B, and C,
B is going to have the same velocity.
Yep, that's exactly right. So we're going to use member one to calculate the velocity at B, and member two to calculate the velocity at B, and set them equal. And then here, we're just going to say there can't be any horizontal velocity. The only velocity has to be vertical along the slot. Okay, so it works just like acceleration, but it's with velocities. Okay, so let's do an example where we can kind of intuitively, okay, so we're going to go, in this case, the velocity at B, according to body one, I don't know, I'm making up this notation, is equal to the velocity at B according to member two. and then the velocity at c, just the x component, is equal to 0. Okay, so let's do an example, and I'm going to do one where we can figure out intuitively. Come on now. Okay, so let's say we have one where at the instant we're looking at, okay, so that's a roller over on the right side. Let's call this member 1. This is member 2. And we're actually not going to get to the forces, but for a problem like this, let's say there's a force applied there. And let's say at this instant, we have an angle of 20 degrees. And the lengths of both of these members are 1 meter. And let's say that omega 1 is equal to, at this instant, well, let's say that at this instant, omega 1 is equal to positive 5 radians per second. It's going to be one of these days. Come on. Do something. So what's omega 2? Okay, so I chose a positive value of omega 1 just to be contrary. How is it possible that, so positive means that omega 1 is counterclockwise. So this thing is standing up straighter. How is it possible that this system, with that force acting there, could have an angular velocity of, any counterclockwise angular velocity? Yeah, exactly. So, So this free body diagram is instantaneous. And instantaneous stuff affects accelerations. Okay? Velocities only deal with accelerations as like an integral over time. Okay? So clearly the angular acceleration of this is going to be clockwise. There's no way around that. But we could think of this as right up before this instant, there were forces pushing this up. And right at that instant, those forces disappeared and that 500 is applied. Okay. And the angular velocity just doesn't change instant by instant with forces. Only acceleration does that. Okay. So just remember that those angular velocities are telling a story about what happened before. It's the angular acceleration that tells the story of what's happening at this instant. Okay. Okay, so we want to calculate omega 2. And this is an isosceles triangle, so we know this angle is also 20 degrees. And so if you think of this angle as like theta 1, And you think of this angle as theta, that's not a theta, theta 2, okay? Then think of the definition of the angular velocity. So the angular velocity of 1 is going to be the time derivative of theta 1 as a function of time. Okay. And the angular velocity of 2 is going to be, well, I have this measured from the negative x-axis clockwise. So this is just going to be negative d dt of theta 2. Okay. And theta 2 always has to be equal to theta 1 in this simple case that I've come up with, where this is always going to be an isosceles triangle with those two lengths are going to be the same. Who's still listening? Okay, good. The rest of you, ask your friends about this after class. Okay, so if theta 1 and theta 2 are the same, then omega 2 is equal to d dt of theta 1. And so what this says is theta 2 is just equal to negative, omega 2 is equal to negative omega 1. Okay, that just has to be the case at any instant. So reasoning through it in this way, in this simple case, so we expect that omega 2 is going to be equal to negative 5 radians per second at the given instant. Okay.
That's just because the angles are the same.
Because what?
The angles are
Yeah, because at every instant the angles are the same, so the derivatives have to be the same.
This wouldn't be the case if it wasn't isosceles.
Exactly. So in this example I drew up here, where those angles are not the same, then it's more complicated. But you would do the calculation the same way. This is just one where we know going into it what to expect for an answer. Okay. So now we're going to do the calculation and see. So we better get that omega 2 is equal to negative 5, or I quit. Okay, so we're going to go, so first we're going to do a velocity constraint. Oh, so we have 1 and 2. Let me call these joints A, B, and C. And I'm going to start with a velocity constraint at B. So according to member 1, I mean, notice how similar this is to the joint constraints that we use in solving this linkage. So looking at member 1, that point B on member 1 is just in circular motion around A. And so we're going to use the velocity equation. So the velocity of that point B is equal to omega cross R. And the omega vector is equal to 0, 0, positive 5. And the R vector from the center of the circular motion to the point B is the length 1 times cosine and sine of 20 degrees. So that's 0.940, 0.342. And so according to member 1, the velocity of B is equal to 0.005 crossed with 0.940 0.3420. And we get negative 171. So that is negative 1.71. And then 4.700. Okay? With me on that? And now we'll go to member 2. So according to member 2, we don't have a fixed center of a circular motion. So I'm going to use relative motion. So I'm going to, like I do with acceleration, I'm going to use the center of mass here. So we'll say that the velocity of B relative to the ground is equal to the velocity of B relative to the center of mass of 2 plus the velocity of the center of mass of 2 relative to the ground. This is going to be two new variables. And this is going to be the circular motion equation for velocity. So the velocity of B relative to the center of mass of 2 is 0, well, I'll write the equation first. So we have omega cross R. And our omega is 0, 0, omega 2. And our R is equal to negative, so this is from the center of mass of 2 to B. So that distance is 0.5 times cosine and sine of 160 degrees. So that's going to be 0.470 negative, and then positive 0.171. So the velocity of B relative to the center of mass of 2 is 0, 0, omega 2. And R is equal, whoop, I already wrote all that. So this crossed with this. And we get negative 0.171 omega 2, and then negative 0.470 omega 2. I'm going to give this a nice name, V2, like we do with accelerations. That refers to the velocity of the center of mass of body 2. And so our constraint equation at joint B says negative 1.71, 4.700 is equal to we have to add this to the velocity of the center of mass of 2. So negative 0.171 omega 2 plus v2x, negative 0.470 omega 2 plus v2y, 0. And so our system of constraint equations, our first one says negative 0.171 omega 2 plus v2x is equal to negative 1.71. Our second one says negative 0.470 omega 2 plus v2y is equal to positive 4.70. Can we solve it? Not yet, but you can see where we're going. So far we have 2 equations, 3 variables. So where are we going to get that third equation? Yeah, the constraint at C. So just like we do with constraint equations at pin and slot joints for acceleration, we're going to calculate the full velocity vector and just set the component equal to 0 that we know isn't moving. In this case, we know that it can't have an up or down velocity, so we'll set the y component equal to 0. Okay. What if the slot in a pin and slot joint was not horizontal or vertical? What if it was at an angle of 20 degrees with the horizontal? Yep. Yeah, I mean, I would think of it as a dot product. Like you could come up with a unit vector that's perpendicular to that slot, and then just set the dot product of that unit vector with the acceleration equal to 0. But you're right, you also could do it by thinking of it as right triangle trig. Yep. Okay, so for the constraint at C, the member that's connected to C does not have a fixed point, and so we're going to use the relative motion equation. So the velocity of C relative to the ground is equal to the velocity of C relative to the center of mass of 2 plus the velocity of the center of mass of 2 relative to the ground. And this one is our V2. We already have that named. And this one is circular motion. So the velocity of C relative to the center of mass of 2 is omega cross r. And our omega is 0, 0, omega 2. And r is, well, it's the opposite of the r that we had in the last one. So that is positive 0.470, negative 0.171. And so the velocity of C relative to the center of mass of 2 is 0, 0, omega 2, crossed with 0.470, negative 0.171, 0. And so that is positive 0.171 omega 2, positive 0.470 omega 2. And so the velocity of C relative to the ground is this plus V2. So we have 0.171 omega 2 plus V2x, and then 0.470 omega 2 plus V2y, 0. Well, we can't make any constraints on x. We don't know what that velocity is. But we know that the y component of the velocity has to be 0. That's what that joint requires. And so our third equation for our system says 0.470 omega 2 plus V2y is equal to 0. And now we have 3 equations for 3 variables. Okay? And if we did everything right, this system of equations should spit out a velocity vector for the center of mass of body 2, which we don't care about, and an angular velocity for body 2, which we expect to be -5. So let's do it and hope. So our augmented matrix has 3 rows, 4 columns. 3 rows. So this is equation 1, 2, and 3. For variables, let's call it omega 1. Nope, there's no, omega 1 is not a variable. We knew what that one was. Omega 2, V2x, V2y, and the constants. So for omega 2, we have -0.171. For V2x, we have 1. For the constant, we have -1.71. Now equation 2, omega 2, -0.47. V2y, 1. And the constant, 4.70. And for equation 3, omega 2, 0.470, V2y, 1, constant 0. We've been doing rigid bodies. You weren't here on Monday, and I was like so conscious, like I better turn this on because no one's going to tell me if I don't. Okay, we've been doing rigid body kinetics and doing that with linkages. Now we're going back a step to particle kinematics and particle kinetics. So remember that here we're just dealing with particles. And I'm going to start with kinematics, but the difference between particle kinematics and particle kinetics isn't much. You know, you're just multiplying by masses, basically. But we're adding a horrifying new bit of complexity. Now we're going to deal with in rotating coordinate systems. Okay, so notice that we're going back from rigid bodies to particles. There are two types of coordinate systems, or let's say there are two ways that a coordinate system can fail to satisfy Newton's laws. Or another way to say that is there are two ways that a coordinate system can be non-inertial. Okay, if you have a non-inertial coordinate system, the measurements that you take in that coordinate system, if you put them into Newton's laws, it's going to look like Newton's laws don't work. Okay, so the first one is that the origin of the coordinate system is accelerating. We're doing classical physics now, so if anybody here who's taking modern physics, this might contradict the way you think about things. In classical physics, there really is such a thing as a true non-accelerating thing. That's a universal property. Something either is or is not accelerating. And if that's your problem with your coordinate system, we've dealt with things like this before. How do you deal with that so that you can come up with numbers that can be used in Newton's laws? Yes, exactly. So we deal with this.
All I'm thinking about is that video.
The Jamiroquai. Exactly. That's what I want you to think about.
Oh, the song. Yeah, sure.
Yeah. Actually, you know what's funny? That just came on like a Pandora playlist or something at our house the other day. And my wife was like, "This is that song you like." And I was like, "Yeah, that's my favorite song for physics." Okay, so we deal with this using relative motion. And we've already done that many times, and it's not too hard to do. The second way that a coordinate system can fail to be inertial is that the axes are changing orientation in time. And another way to say that is it's a rotating coordinate system. So in other words, a rotating coordinate system. And this is the topic that we're covering now. So we'll learn how to deal with this now. What if you have a coordinate system that is rotating and the origin is accelerating? What? It's not extra bad, really. You just have to deal with the rotating coordinate system and then take that answer and use relative motion. So you just have to do both of them. Okay.
First, before relative motion.
Is the stuff that we're going to learn now. Yeah. And one thing I want to make a note of here is, so notice a rotating coordinate system is not just, so a lot of times I think this is the first thing people think of, that you think a rotating coordinate system, maybe that's just a matter of the coordinate axes being misaligned. Like if this thing's rotating, say you have this kind of reference coordinate system that's not rotating, and then this one that you're trying to do calculations for, at a given instant, at a given snapshot, those coordinate systems aren't in alignment. Okay, so is that what we're talking about with rotating coordinate systems? No. That's another thing that you really do have to deal with, but that's just dealt with using a rotation matrix. Okay, and that's pretty quick and easy to do. We're talking about the effects that are caused by, as this thing's moving, say your snapshot happens to be right as those two things are aligned. Okay, then you don't have to deal with any misalignment of the coordinate axes, but you still have to deal with the fact that this has an angular velocity. Okay, so that's what we're talking about. So a rotating coordinate system is not just a matter of misaligned axes. So let's say even at the instant where your rotating coordinate system axes are aligned with your reference axes, the angular velocity of the rotating coordinate system causes, let's call them problems, The angular velocity of the rotating coordinate system causes problems. Well, I like to think of it as the angular velocity of the rotating coordinate system causes opportunities, because those other dummies won't know what to do and you guys will. And that's why people will hire you. Okay, so I want to kind of explain, try to make this intuitive to you a little bit in two ways. We're going to first talk about the math, and then we're going to talk about just sort of an intuitive understanding. So I'll try to give intuition about this. First, mathematically, and second, physically. And hopefully these two things are things you can go back to and remind yourself about when you get confused about what's going on. Okay, so here's the kind of mathematical intuition. So let's say that you're given a vector, we'll call it u, so it can represent anything, a force, a acceleration, a velocity, a position, anything that's a vector quantity. That's what this u can represent. And we'll think of it as, so instead of using the notation that I always use, we'll think about it as what it is. There's a there's a component ux multiplied by some physical unit vector that's just pointing in a direction, plus a component uy multiplied by a unit vector in the y direction, plus a uz times a unit vector k. And the key step, I guess, is what happens when you take time derivatives of this vector u. So the key step is what happens when you take d dt of u. Okay, so d dt of u, or by definition, that's u dot, is, now we have to use the product rule, because for each one of these terms, we have a number times a vector. Okay, and the product rule says this is equal to ux dot times I plus ux times I dot, that's the product rule, plus uy dot times j plus uy times j dot plus uz dot times k plus uz times k dot. And I'm going to regroup. So we get, this gives us ux dot times I plus uy dot times j plus uz dot times k, and then plus ux times I dot plus uy times j dot plus uz times k dot. Okay. So if this vector u is measured in an inertial coordinate system, so if it's not rotating, so if u is measured in a non-rotating coordinate system, then I dot j dot and k dot, well, those are unit vectors in the directions of the axes. So at second 1, one of them is pointing this direction. At second 2, if it's not rotating, then it's in the exact same direction. So those are all equal to 0. Okay, are you with me on that?
Can you draw something for can you draw something?
Yeah. So you can think of your unit vector I is this, your unit vector j is this, and your unit vector k is this. Okay, this is at instant 1. Okay, at instant 2, if it's not rotating, then these aren't going to change. That's what not rotating means. And so if things are not changing in time, then the time derivative is 0. Okay, and so what that means is this second set of parentheses goes away, and our u dot is just equal to the first one. Or in other words, it's exactly what we saw in the past. To put it back in our notation, it's just this. It's easy. Okay. But if this vector u is measured in a rotating coordinate system, okay, then at instant 1, our I is this way, our J is this way, our K is this way, and at instant 2, our I now is this way, our J is this way, and our K is this way. So that means that I dot is not equal to 0, J dot is not equal to 0, and K dot is not equal to 0. And that's a problem because what are these things? You know, we don't have any way to represent those. So, and that's a problem because we don't know what these are. Okay, so where does the, so just a review of what we're talking about. So you can define that vector u in a non-rotating coordinate system or rotating coordinate system. There's no problem with that, okay? The problem comes when you do what to that vector? Yeah, when you take that time derivative, that's when the problem comes in. And so we need a way to correct our time derivatives. So what we need is a way to correct our time derivatives for vectors measured in rotating coordinate systems. Okay. So now that is the mathematical intuition. So now we're going to do the physical intuition. And I actually think that I've drawn this out before, but we're going to do it again. So this is the centrifuge thing that they use to train astronauts and fighter pilots to deal with high Gs. Big accelerations. So if you think of 1g as 9.81, we're dealing with many times the acceleration of gravity. So 20 meters per second squared, 30 meters per second squared, 40 meters per second squared. In a high performance fighter jet, for example, you can experience many times that. And you have to train yourself not to go unconscious because they don't care so much about the pilots, I don't think, but they don't want to smash their planes into the mountains. So they have to train their pilots so when they're in these really extreme maneuvers, they can keep from blacking out as that acceleration forces their blood away from their brain. And so what these things look like is, so you have like a hinge in the center of the rotation and a long arm with a chair at the end of it or some kind of something that the pilot can sit in. And then the pilot is in this chair. And this spins around, and the pilot spins around. Like that. Yeah, it's got to be unpleasant. And what we're going to imagine is that there is a camera, a video camera. This video camera is our coordinate system. And this video camera can do two things. So it functions as our coordinate system. Let me draw the, so let's say our x-axis is going to be this way. Our y-axis is going to be up. And our z-axis is going to be like that. But this camera can do two things. So the camera can stay fixed in that orientation. Or it can rotate with the arm. So if it rotates with the arm, that means that it's always looking at the pilot. Okay. And let's, so I think in Physics 1 lab, you did things where you sort of took finite measurements close together, and you did what essentially is a numerical calculation of velocity and acceleration from looking at positions, right? You used a difference equation instead of a true derivative, and you thought, like, if we do them at close enough instants to each other, this difference equation that we're going to use is going to give us a similar answer to a derivative. Okay? So we're going to think about successive frames of what this video camera sees in both of these two cases. Okay? And we're going to think about what that means for the derivatives. So first we're going to think about that camera with the fixed orientation. And we're going to think about three frames that are relevant to calculating the velocity. So the first, if you think of this as like a film strip that we're looking at from left to right, So the frame on the left is the first picture the camera takes. The middle one is the middle picture the camera takes, and then the last picture the camera takes. So the first relevant picture the camera takes is the guy just coming into the frame. The second one is the guy right in the middle of the frame. And then the third one is the guy leaving the frame. Okay. So the position that's measured by this camera changes as time goes by. Okay. So clearly, the estimate of the velocity vector from these frames is non-zero, right? And you could do this one more time and estimate the acceleration. You'd get a non-zero acceleration. Then you could put that into Newton's laws. Say that this chair had force sensors in it. Okay, those force sensors are going to read big values as this centripetal acceleration gets bigger and bigger, spinning this guy around, right? So if you combine what the force sensors in the chair say with what you measure for acceleration in this non-rotating coordinate system, you get a match between those. Newton's second law appears to hold. So let's just go same with the acceleration. And so Newton's second law holds for these measurements. Okay, so now we're going to do the camera rotating with the arm. And we'll do the same thing again. Think about this film strip with 3 frames. So now in those same 3 instants, what does the camera see at instant 1, the first relevant frame? Yep, it sees the person right in the middle of the frame. Most of this example is just drawing this guy. Yeah. What does the camera see in the second frame? Okay. You get it. And then in the third frame, same thing. And it's that way for the full rotation around, you know? So for the rotating coordinate system, the estimate of the velocity is 0, which we know is not true. And it's the same with the acceleration. And that means that Newton's second law, I mean, that force sensor is still reading the same values, the same non-zero values. So Newton's second law does not hold for accelerations measured in this rotating coordinate system. Okay, so that's what we're dealing with. We need ways to correct the accelerations that we measure in rotating coordinate systems because there's this fundamental problem. And that fundamental problem comes mathematically from these, not those, from these u dot, j dot, and k dot not being equal to 0. Okay. Okay, so we need to correct time derivatives taken in rotating coordinate systems. Okay, so that's the bottom line here. Anytime, if we're just measuring something at a single instant, that's fine. The coordinate system can be rotating. But if we want to take a time derivative, then we have a problem that we have to deal with. And so I'm just going to give you this result. And next class, I'll give you a little intuition about it in 2D at least. So to correct this, here's what you use. And I'm going to call this the big result. This is what everything else in this section comes from, the big result. So if a vector u is measured in a coordinate system that's rotating, with an angular velocity of this thing. Anyone know what Greek letter this is? Omega. Have we used omega before?
Not the lowercase.
The lowercase one, yeah. So there's a reason that we're still using omega, but we're using a different omega. It's similar to what we've used before, but it represents something different now. Okay, so this is something that you're going to want to keep straight, which of these two omegas we're talking about. But if your coordinate system is rotating with an angular velocity of capital omega, then u dot, your time derivative of u, is equal to ux dot, uy dot, uz dot, plus capital omega crossed with the u vector. Okay. There's another way to say that, and each one is useful in its own setting. So in other words, these aren't words, I guess, they're equations, but u dot is equal to what the coordinate system thinks u dot is. So I'm going to write OBS for observed, the observed time derivative, plus the angular velocity of the coordinate system crossed with u. This is the big result. Everything is going to be based on this. Well, what is u? Is that a position vector, a velocity vector, an acceleration vector, a force vector?
Position vector.
It could be anything. It's true that for us, a position vector is going to be an important thing, but this is true for any vector that you measure in a rotating coordinate system. But now what we're going to do is we're going to apply this derivative rule to position vectors to come up with a corrected velocity vector and a corrected acceleration vector. Because really, the key thing for us are these acceleration vectors. That's what we put into Newton's laws.
So it's like a new channel?
It's like a, I guess you could think of it as maybe like a new relative motion in a way. Like it's a rotating relative motion equation where this first piece is what we're used to for time derivatives, the first term, and the second term is like our additive relative motion term. Okay. Any questions about that? Okay. I won't give you an assignment. We have a test on Monday. And then in a week, on Wednesday, I'll go through a little derivation, and then we'll start going into how to use this in problems. Okay, that's all.